All right, gang, Math 6610, transitioning into non-parametric statistics. And intentionally, I kept this for lesson number 7. A couple of reasons for that. Number one, this is the final lesson, and I found that teaching under the 7-week format, that the last week is pretty insane. So it kind of made sense for me to keep the maybe the easiest material for last, and there's probably going to be less instructional videos because once we get experienced with the Anova techniques, as we've done, you may argue ad nauseum with repeated measures and two-way Anova, factorial Anova, one-way Anova, ANCOVA. We should be pretty good at this by now. So anyway, that's the logic behind leaving non-parametric tests to lesson number 7. So just going to run through a quick example here. Again, we should be pretty good at this stuff. So it's just kind of a slight modification for what we've done previously. So non-parametric tests are just what a lot of people call a distribution-free test. Let's be complete. And when we violate assumptions for a standard parametric test, if you will, then we should consider using non-parametric test. We should definitely use non-parametric test when we have data that's been collected using a survey or some measurement similar to that. So, Likert data, agree, disagree, strongly, all that stuff. So recall the p-values are calculated using this underlying probability distribution. Think back many moons ago, lesson number 1 specifically, where we dove into the central limit theorem. And just remember, when we violate our assumptions that lead up to this probability distribution, again, from which we calculate our p-values, if we violate the assumptions, then our p-value calculations are not stable. So we need a correction method, and that correction method, or I should say we need an alternative, and that alternative is non-parametric test. So we're going to learn in this class only 3. There are far more, but what I want to present to you, because I feel like if we get a foundation of these 3, we can move into some other designs very easily if you encounter that in your the research for your master's thesis. So the equivalent of a parametric 2-sample t-test, independent samples t-test, is something called a Mann-Whitney test. Dependent samples t-test, we have a paired samples t-test is the Wilcoxon signed rank test. And then the one-way Anova equivalent in the non-parametric world is the Kruskal-Wallis test. There are others. A correlation, for example, Pearson correlation, which is a parametric test, has its own non-parametric version. Repeated measures that we studied a couple of lessons ago, Friedman's Anova, is the non-parametric equivalent to that. So when to use? Well, if violations are, I would say we have extreme violations to the assumptions, then we should consider parametric tests. Now, I don't want you to throw the baby out the bathwater, and if you're running a standard Anova design and you violate well, if you violate independence, then you can't proceed. But if you violate slightly normality and violate slightly, and/or I should say, equal variances, then oftentimes, and the research actually says that we should proceed with standard Anova, parametric Anova design. But the one time when you cannot proceed in the parametric world is when you have ordinal data, and again, just think Likert scale data, or obviously categorical. So disadvantages to non-parametric techniques: you lose statistical power when compared to parametric tests when the assumptions are not violated. And some people say it's just not as cool. I have to tell you, I kind of fall into that world uh, unfairly and certainly not validated. I think non-parametric tests have their place in time, and I just I did. I remember I helped a lady. She worked with a mattress company, and they were doing some survey data on some mattress and a new design, and she was actually analyzing this data for her dissertation, and I helped her, and we were just, because again they were analyzing data from a survey, we were forced into the non-parametric world, which it just is what it is. So the process for, and I want to focus on the Anova, the Kruskal-Wallis Test. So the process is we rank our data and then we sum the ranks over each level. And this is a little tricky, and I'll explain that as I go through the example. We calculate a test statistic, which is one of the more complex. Well, I don't know, compared to Anova, it's probably not that complex, but you just sum up the ranks and square them over the individual in sub i's, and then we calculate the p-value based on the chi-square distribution. If k is the number of levels in our independent variable, again, think Anova world, then our chi-square distribution is degrees of freedom k minus 1. Now, let's just run into a quick example. So what I have here is a standard Anova design, because I'm interested in the scores across. And let me explain what these are. These scores are actually a feeling. I forget the scale, but there was some questions, and they summed up the scores on these questions under Likert scale to try to get indication of how the student feels about being included in their district. Rather large sample size. You can see I have 162. We have a balanced design, meaning that the number of students from each district is the same. And the t apply gives us the mean across. So I don't, well, it does kind of look like that the students from District E have a higher feeling measurement, average feel measurement than for District W. So what I would probably want to do first is let's just explore some of the assumptions. So I would do a Shapiro. I tell you what, let's do it this way. Let's do a score across district, and let's do a Shapiro test to test the normality assumption within each district. And you can see that we fail miserably, and we fail. So we cannot proceed with the normality assumption. Let's just look at equal variances. So we know we have to load car package. And so the Levine test, again, score over district. And you may imagine this is going to be statistically significant, because it would be kind of goofy for me to demonstrate the need for a non-parametric test when there's no violation. Plus, again, really, I think just the design of the study trumps all of this, because we have Likert data. These bits of scores have been taken from a Likert scale and summed up. So the next thing we want to do is, because these non-parametric tests use sums, and so I need to rank our data. So it's really easy to do. I'm just going to call it ranks. So I want to rank the scores. I always forget whether it's score or scores. And then I want to create a new data set. So I'm going to create a new data frame, and I want my ranks, and I want my score, and I want my district. All right. So I'm going, and I need to attach it. Now, what, and I hate to clutter this up, but I want you to see the entire data set. What they've done is they've given ranks. So, and I think from someone who follows a lot of college football, I think the ranks are a little goofy here because of the way it ranks all these scores of 0. Now, these are the lowest. So, for example, if we have 2 college football teams and they're tied for number 1, well, we give them both 1s, right? And then the team that comes in technically second place, I guess technically third, they would get a 3. Well, R does this a little differently. That's a rabbit hole I really just don't want to go down in, but nevertheless, there are the ranks. Now, I can look at, I'm going to need the sum of the ranks. Let's see, did I thought I gave you, oh yeah. So I need the sum of the ranks, so I can do T apply, ranks over district, and do sum. So there are the sum of the ranks in each district. Now I can calculate the test statistic, and let's just do that. It's going to take a little bit of work. It's going to drive me insane, but it is what it is. Now I need my total sample size, so 162. So my H is going to be equal to 12 divided by 163. I don't think that's right. No, that's not right. I got sloppy there. Make sure you make that correction. I got very sloppy. So I need 162 times 163. All right, then I need times the rank squared for the first, so 4092 quantity squared divided by what was it, 50? It's a little clumsy here. 54. And I need that. All right. And I need to sum up. So 5356.5. Quantity squared divided by 54. I should have just factored that out. And then 3754.5. Quantity squared divided by 54. All right. And then I need to subtract 3 times n plus 1, so that would be 163. I hate doing this kind of stuff. But I just want to run through one of these for you. Now we get H as 12.0042, and again, take this with a grain of salt, the way that R calculates the ranks. I think it's questionable, but I certainly don't want to go through this problem by hand and calculate the ranks because we have bigger fish to fry than this. So if I wanted to calculate my p-value, I would go 1 minus because I need the upper tail in the chi-square distribution. So I need H, degrees of freedom 2 because I have 3 districts, and I get a p-value of 0.00247. This is a pretty good approximation, not bad. Well, it turns out, as you may imagine, that there is an option in R to run this directly. So it's just called the Kruskal Test. We're going to run score over district. It's going to do all the calculations of the rank sums behind the scenes. And let's make sure we have the right data set. So our p-value, our Kruskal-Wallis chi-square test statistic comes out pretty close, 12.1 versus 12.0, degrees of freedom 2, and notice our p-value is pretty close. So we would reject the null. So again, the null here is that the median ranks are the same across district. Versus the alternative, the median ranks are not the same across district. I shouldn't say the median ranks, I should say the medians are not the same across district. The rank is the process we do to create the test statistic. Now, I would want to follow up, since we have this model that is statistically significant, I'd want to follow up with a pairwise test. So I'm going to use the pairwise Wilcox test. Now, the Wilcox is the independent samples t-test, as we well, actually, it's a dependent samples t-test, but this allows us to conduct the post hoc. So I need score, district, and the p-adjust method that I would use in this is the BH. So I get the p-values, and I can see that there is a statistically significant difference between districts C and E, and there is a statistically significant difference between E and W. So if I go back up to my means, wherever they are, so the difference between E and W is statistically significant, and the difference between C and W, I think I got that right. E and C and E and W. Yeah, E and C, E and W. So E and C and E and W. So for some reason, the students at District E feel an awful good about themselves, which is obviously a good thing. All right, that's all I got. Take care.